Being able to draw a Lewis dot structure is just as important for an ionic as it is for a covalent, although it is significantly easier. As a very quick review of how to find the number of dots, which again represent the number of valence electrons and each individual atom will have, let me just go ahead and quickly draw my little periodic table over here. So remember that the valence electrons all go by what group or what family the element belongs to. So the very first, called the alkali metals, have 1 dot. These have 2 dots, the alkaline earth metals. The boron group has 3, carbon group has 5, nitrogen group has 5, oxygen group has 6, halogens have 7, and of course the noble gases have 8. So any element within that group is going to have that number of dots because that's the number of valence electrons that that atom would have. Now, do remember that, of course, that an ionic bond is between a metal and a nonmetal. Therefore, we're going to have one from the left side of that zigzag. All of these over here are going to have a positive charge because they're going to lose electrons. And all of these over in the top right are going to have a negative charge because they're going to gain electrons. Therefore, we're going to have a attraction of opposite charges, the positive metal and the negative nonmetal, and that's what's going to hold the ionic bond together, is that attraction of opposite charges. It's surprisingly a very strong bond, much stronger than covalence. I do want to remind you guys very quickly again that hydrogen over here is a nonmetal. It is a gas. Therefore, if a compound starts with hydrogen, it is not going to be an ionic. It's probably going to be an acid or a covalent. So please don't forget about them. And of course, the octet rule says that all the noble gases will also not be involved in a bond. So you can kind of ignore them too, because of course they have the 8 that they required, or helium has 2. Therefore, they're not going to bond. So what we're talking about is anything left of the zigzag except H, which would have a positive charge, bound to anything to the right of the zigzag except the noble gases because they have a charge of 0. Otherwise, other than those exceptions, you have a metal and a nonmetal, always in that order, a metal first and a nonmetal second. But I'll show you that in just a moment. But first, let's go ahead and review these Lewis dot structures. So sodium, again, is an alkali metal. It's in group 1, so it's going to get 1 dot. Magnesium's in group 2. It's going to have 2 dots. Boron is in group 3. It's going to have 3 dots. Carbon has 4 dots. Nitrogen has 5 dots. Oxygen has 6 dots. There we go. And fluorine has 7. And of course, neon has 8. And again, because it has the octet rule, has the octet already. That's why it's not going to bond at all. So there you go. So it's really quite simple. Again, it's all determined by where it's located on the periodic table, what group it's in will tell you how many valence electrons it has, and therefore the number of dots to put on that particular element. Now, again, the octet rule states that all elements, or I should say atoms, let's just say, I'm going to use the word want. Now, again, I don't like the word want because these are atoms. They don't have consciousness. They don't have a desire, but they're all going to do something in order to get 8, let me say, valence electrons. Now remember, with a covalent, they're going to share them, right? In a covalent, there is no give and take. There is no positive negative. It is a sharing, whether it's equal or unequal. Again, that satisfies the polarity question, but they're still going to share in order to get the 8. In an ionic, it's a little different because you're going to have something that's very electronegative, which is the nonmetal. Why it's going to become negative. And then you have the less electronegative element, in this case, the metal, which is going to become positive. And again, so one is going to steal, the other one's going to lose. Whereas covalents, again, just to repeat myself, are sharing their electrons. So again, rules for drawing Lewis dot structures for compounds and polyatomic ions. I'll talk about those things in just a moment. But we're going to count the total number of valence electrons in the compound, determine whether the compound is ionic or covalent, and if the bonds are ionic, we're going to use brackets to show the charge that the ions are separate. So again, there's a little example right there. So the very first example we have here, it says, draw the Lewis dot diagram for a compound between sodium ion and a chlorine ion. So sodium, again, is going to be Na. It has 1 dot. Okay. Then we have a chlorine ion, really called a chloride. it's going to have 7. 1, 2, 3, 4, 5, 6, 7. All right, and then basically what's going to happen is, as you could probably tell, the chlorine is more electronegative. It's in the top right of the periodic table. It really wants that electron right there, right? And sodium is more than happy to give up its electron, because then it would no longer have that outer energy level, because it would be empty. It would basically be non-existent. So the next inner one, which would become its new outer energy level, would automatically already be full. So therefore, its um, final Lewis dot structure would be sodium with 0 dots. It would have a +1 charge. Again, plus and +1 are the same thing. And then chlorine would be over here. It would have 8 dots, and it would have a negative or a -1 charge. That right there on the right side is the Lewis dot structure for a sodium ion and a chloride ion, which again is a ionic bond. The cation on the left, metal, anion on the right, which is the nonmetal, again, and their attraction to each other. All right, so that's the first example of ionic bonding.